Hi, good evening. I am Ritu KP from CC department CC2A section. Today I am doing presentation of operating system of second assignment based on the topic Robin round problems statement. This is the first page of the assignment. So our subject coordinator is Usha TM ma'am. So let me go with the introduction. So let us start with the introduction. Introduction of our topic is CPU scheduling is one of the most essential functions of a modern operating system because it determines which process gets access to the CPU at any given time. Since multiple processes often coexist in memory and compete for CPU time, an efficient scheduling policy directly impacts systems responsiveness, throughput, fairness, and resource utilization. Among many scheduling algorithms, round robin is particularly well suited for time sharing and interactive systems. Each process a fixed time slice called the time quantum after which the CPU is preempted and process is placed at the end of ready queue if it has not finished. The choice of quantum is critical to a small leads to excessive context switching overhead while too large a quantum causes poor responsiveness and makes the CPU behave more like a non-primitive scheduler. The objective of this experiment is to design, implement, and analyze the round robin scheduling algorithm with a configurable quantum and evaluate its performance using different quantum sizes. By observing that variations in waiting time, turnaround time, response time, and context switching across multiple quantum values, we efficiently quantum size for the given process data set. Experiment with at least four quantum size on the same process set and determine the best quantum value with justification. So let me continue with the next part. Next part is experimental steps. Here is the experimental steps. The experiment was conducted using a fixed data set of five processes, each having predefined arrival times and CPU burst durations. These processes are intentionally varied in size to observe the effect of premission and time slicing using the Java programming language chosen for its probability, object oriented structure, and ability to stimulate process states using classes and queues. The round robin scheduling algorithm was executed multiple times, each with a different quantum value specifically, and for each quantum, the scheduler simulated the flow of execution and matrices such as completion time, turnaround time, waiting time, number of context switches. The program printed a step by step timeline indicating which process ran during each CPU interval, allowing for the manual construction of Gantt chart after all runs were completed and the matrices were compared to observe the effect of different quantum size on overall system performance. Approach allowed a fair, controlled comparison to justify the most efficient. So let me go with the next part. Implementation steps. Next part is here is the next part. The round robin scheduler was implemented in Java using an object oriented approach. Each process was represented using a process class contained its PID, arrival time, burst time. Like we can call them in a short TT, WT, RT. So remaining time, completion time are calculated. A ready queue was implemented using a linked list reflecting the FIFO nature of round robin. The scheduler first sorted all processes by arrival time, then stimulated by the passage of time, adding process to the ready queue as soon as they repeatedly dequeued the first process, executed it for either the quantum or its remaining time, and then either rain started it at the rear of the queue was marked and it is completed. response time was recorded when a process ran for the very first time. At every step, newly arrived processes were also added to the ready queue, mimicking real world dynamic arrivals. After all processes completed, the program calculated and printed average waiting time and turnaround time and responses time. This step by step event driven implementation closely resembles how real operating system manages. Next is the flow chart. Here we can see how shortly we designed the flow chart. Ready process quantum, we initialize it to 0, then yes or no, like how it divides. Ready attempt, process finished, all done and all. So let me go with the next part is the Java program code, the handwritten code. We can search and design a simple Java code to the round robin problem. So you can see it is a basic Java program. Starting of this, we need to include import java.util class. We need to create classes, and we have used this keyword public class we have mentioned. And the next page we can see the main program. Here is the main program comparatively about the conditions, and the next is the output process like system dot and all. So next is the output. Here we can visible that times and processes, like how we took and the Gantt chart, and also calculated table and also average time, waiting time, turnaround time, response time, and also context switches like 7. So here is the output of the program. So next part is observations. So let me go with the observations. From the results obtained during the experiment, it became clear that the value of the quantum had a significant influence on CPU behavior and process performance. A very small quantum, such as 2, caused frequent preemptions, resulting in many context switches. Although this improved the responsiveness of short process, it also increased overhead and had a slightly negative impact on waiting time and turnaround times. When the quantum was increased to 4, system performance improved noticeably. Average waiting time, turnaround time, and context switches are well balanced, making it the best performing quantum for this dataset. Larger quantum values such as 6 and 8 reduced context switching, but at the cost of increasing wait and turnaround time, short processes to wait unnecessarily behind long ones. Across all results, it became clear that a moderate quantum provides the best compromise between fairness, overhead, and responsiveness. So, next part is the comparative evolution. Here you can see I have uploaded a table, so through which we can compare the FCFS, SJF, SRTF, so with D1, D2, D3, and also performances of the matrices. So comparing the performance matrices obtained from the different quantum size highlights the trade-offs inherent in round-robin scheduling. A quantum of 2 time units produced the highest number of context switches, which indicates excessive permission and overhead, even though responses times were favorable. Quantum 4 produced the best overall results, yielding the lowest average waiting time. So this balanced behavior demonstrates the quantum 4 is neither too small overhead or not too large degrade responsiveness. Quantum numbers that we choose the comparative analysis clearly demonstrates the mid-range quantum values achieve the optimal balance between fairness and CPU efficiency. So next part is the conclusion. So which I need to conclude my second assignment of operating system. The round robin scheduling algorithm provides fairness and responsiveness in time shared operating systems, but its performance depends on heavily on selecting an appropriate quantum size through the implemented Java simulation and systematic experimentation across multiple quantum values. The results demonstrate that a moderate quantum, specifically 4 of the given dataset achieves the best balance between minimizing waiting time, reducing turnaround time, maintaining good responses times, and keeping context switches overhead manageable. Extremely small quantum values cause high overhead due to excessive preemptions, while large values reduce responsiveness and cause the algorithm to degenerate toward FCFS behavior. Therefore, choosing an optical quantum must be adapted to workload characteristics. This experimental not only validates the behavior of round robin scheduling but also highlights the importance of careful parameter tuning for real world operating system performance. So, thank you.